The Chinese continue to make some spectacular gains out in outer space. Today, sending back some...
For the first time, China has revealed powerful discoveries from the moon's far side, the hidden face locked away from Earth forever. Beneath the dust, they found clues that challenge old space theories and raise new questions about our universe. What secrets did the moon keep hidden? How does this discovery change science? Join us as we uncover the truth. Touching the hidden face of the moon. The far side of the moon stayed beyond human reach for a very long time, not because of distance alone, but because of silence. Space is quiet in a way that blocks help, guidance, and rescue. The moon is tidally locked, which means it turns once for every orbit around Earth and always shows the same face to our planet. While it slowly drifts away from Earth by about 4 centimeters each year, its opposite side remains hidden behind solid rock. Radio signals cannot bend around that barrier, so any signal sent toward the far side is stopped completely. This communication blackout explains why no Apollo mission ever went there, and why the Soviet program could not land a rover that could be controlled in real time. A machine can touch down, but without a live connection, it cannot be guided, corrected, or saved when danger appears. Even a small sensor mistake can turn into total failure. China solved this problem long before attempting a landing. In 2018, it launched the Kuo Relay satellite, a name that means Magpie Bridge. The satellite was placed near the Earth-Moon L2 region in a halo-style path, where one side could always see Earth and the other could see the far side of the moon. This position created a communication bridge across space. Commands could now pass back and forth like a quiet message slipping through a locked door. With that system ready, Chang'e 6 lifted off on May 3, 2024 with one clear goal: reach the hidden ground of the moon and bring part of it back to Earth. There was no joystick and no pilot guiding it directly, only systems designed to think and act on their own. Even with communication solved, there were moments when the lander had to survive completely alone. The most dangerous part of the Chang'e 6 mission was not launch or return, but the final descent. The target was the South Pole Aitken Basin, a massive wound on the moon that stretches about 1,500 meters across and drops nearly 5 meters deep. This basin was formed more than 4 billion years ago by an impact so powerful it almost cracked the moon's crust. Scientists selected this location because it exposes layers that no human technology had ever touched before. Those same features also made it one of the most difficult places on the moon to land safely. As the lander began its descent, Earth lost the ability to guide it in real time. For about 15 minutes, Chang'e 6 was completely on its own, falling toward rough and uneven ground filled with deep shadows, steep slopes, and rocks as large as cars. Commands sent from Earth arrived too late to help. Every choice had to be made by the machine itself. Instead of a human pilot, onboard artificial intelligence scanned the surface while descending, comparing live images with hazard maps created from orbital data. Each second, the system adjusted thrust, changed angles, and ruled out unsafe landing areas. All of this happened while fuel steadily burned away and gravity pulled the spacecraft closer to the surface. One wrong calculation would have ended the mission in an instant. The final approach was especially fragile. Dust kicked up by the engines interfered with sensors, while the moon's low gravity made every movement harder to predict. At this stage, even a small bounce could have tipped the lander over or slammed it into uneven ground. Still, the guidance system continued making careful corrections. It chose stability instead of speed, slowing and adjusting until the landing legs finally touched the ancient surface. When contact was confirmed, the basin stayed silent, but the mission had crossed a line many believed could not be crossed. Chang'e 6 did not remain idle for long. Within hours, its drill reached into soil that had not moved since the early days of the solar system. It bored into layers shaped long before Earth had stable oceans. A robotic arm followed, collecting surface material and placing it into sealed containers built to survive the long journey home. Every action mattered because time was limited. The far side of the moon is an unforgiving place, with extreme temperature changes and no natural protection from radiation. The lander gathered what it could, and then prepared for the most complex task of the entire mission. Launching back into lunar orbit from the far side had never been tested before. The ascent vehicle ignited smoothly and lifted off, leaving behind a fresh mark in a basin already scarred by billions of years of impacts. It met the orbiter above the moon, transferred its precious cargo, and sent the return capsule on a long path toward Earth. The landing site disappeared from view, but its importance was now sealed inside strong metal walls. 53 days after touching the far side, the capsule entered Earth's atmosphere and landed in Inner Mongolia. Inside were nearly 4 pounds of lunar rock and soil, collected from the deepest and oldest crater on the moon. The mission had survived every risk placed before it. When scientists finally opened the container, the first surprise was clear right away. The samples did not resemble the pale dust brought back by Apollo missions. Their darker color suggested a different history and raised a powerful new question. What had this impossible and hidden place been holding for so long? The moon's two faces and the hidden heat within. The sample from the far side of the moon appeared darker than many scientists expected. That small visual detail pointed toward a much larger truth about how the moon formed and evolved. When people look at the moon from Earth, the near side feels familiar. It is marked by wide, dark areas called Maria. The word comes from Latin and means seas, even though these features are not made of water. They are frozen lava plains. Long ago, basalt erupted from below, flowed across low areas like spreading ink, and then cooled into smooth surfaces. These plains reflect less sunlight, which is why they look dark from far away. The far side of the moon looks very different. It is brighter overall, higher in elevation, and much rougher. Craters sit on top of other craters, creating a crowded and uneven surface. There are almost no wide lava seas to soften the view. This strong contrast between the two halves is known as the lunar dichotomy. It suggests that the moon followed two different thermal paths, starting very early in its history. For many years, scientists could clearly describe this contrast, but they could not test the deeper cause. They lacked fresh rock samples from the far side, which remains hidden from Earth. This is why Chang'e 6 was so important. It did not only return soil, it returned a clue from a region tied to the oldest scars on the moon, where ancient impacts and buried layers come together. The landing area for Chang'e 6 lies within the South Pole Aitken Basin. This structure is about 2,500 kilometers across, making it one of the largest impact basins in the solar system. Its great depth turns it into a rare window into material influenced by the moon's interior. When scientists compare the chemistry of lunar samples, they focus on a special group of elements known as CREEP. The name stands for potassium, rare earth elements, and phosphorus. These elements matter because many of them are linked to radioactive decay. Over immense spans of time, that decay releases heat. In this way, CREEP acts like a slow internal heater. Samples collected during the Apollo era from the near side, especially from the Procelarum region, showed stronger signs of this heat-producing mix. That evidence fits the idea that one half of the moon had a warmer engine beneath its crust. When this idea is placed beside what is known about the far side, the contrast grows clearer. According to NASA, the lunar crust is about 40 kilometers thick on the near side, but around 60 kilometers thick on the far side. That extra thickness works like a heavy lid. It makes it much harder for magma to rise and break through to the surface. A more recent analysis based on gravity measurements adds more support to this picture. It suggests that the moon's interior is uneven, with the near side mantle estimated to be roughly 100 to 200 degrees Celsius, warmer on average than the far side. In simple terms, one half of the moon stayed more willing to melt. Because of that, molten material reached the surface again and again. Over time, this process built the Maria that people recognize so easily when they look up at the night sky. The samples returned by Chang'e 6 add an important new layer to this understanding. These materials come directly from the far side, which allows scientists to compare them with Apollo samples and with materials from Chang'e 5. Reports connected to laboratory work on these samples indicate that the source regions on the far side were cooler during lava formation than similar regions on the near side. This finding strengthens the idea that the moon's internal heat was never shared evenly. The difference was not short-lived. It lasted for billions of years. With this view, the story of the moon shifts away from surface appearance alone. It becomes a story about a deep internal imbalance. The moon is not a single world with one uniform interior. Instead, it is a body made of two geological personalities joined together. The near side had more internal heat and a thinner crust. These conditions allowed lava to reach the surface and spread widely, creating the dark morea that dominate the familiar face of the moon. The far side had less of the heat-producing mix and a thicker crust. As a result, it kept its bright highlands and preserved its long history in heavily battered stone. The quiet discovery of natural graphene. At first glance, the dust that covers the moon looks simple and harmless. It appears dry, gray, and lifeless. But when scientists study this dust closely, especially under powerful microscopes, it reveals surprising secrets. Inside this fine lunar soil, also called regolith, researchers have found structures that humans usually must create very carefully on Earth. One of the most surprising of these structures is graphene. Graphene is a form of carbon arranged in extremely thin sheets. These sheets are so thin that they are only a few atoms deep. On Earth, making graphene is not easy. It usually requires strict chemical steps, very high heat, or advanced machines designed to peel away carbon layers with great care. The goal is always the same: to isolate carbon sheets that are just a few atoms thick. Because of this difficulty, the idea that graphene could already exist naturally inside moon dust seems almost unbelievable at first. However, scientists studying lunar samples returned by China reported finding natural few-layer graphene within the regolith. This graphene appeared in two main forms. Some of it existed as tiny flakes scattered through the soil. Other pieces formed carbon shells that wrapped around small mineral grains. These structures were not thick chunks of graphite. Instead, several studies described sheets made of only 2 to 7 layers of carbon. At this thickness, the material behaves like graphene rather than ordinary graphite. To confirm what they were seeing, the research team used electron microscopy along with other supporting tests. These tools allowed them to study both the structure and the chemical makeup of the carbon. This step was very important. It helped reduce the chance that the carbon came from contamination during laboratory handling on Earth. The results supported the conclusion that the graphene truly formed on the moon and was not introduced later. This finding raises a natural question. How could graphene form on a world with no air, no water, and no living chemistry? The answer lies in the harsh and violent environment of the lunar surface. The moon has no atmosphere to protect it. Every day, it is exposed to radiation, vacuum conditions, and constant impacts from space. Micrometeoroids strike the moon at extreme speeds because nothing slows them down. Even tiny grains as small as sand can deliver massive pressure for a brief moment when they crash into solid rock. In that instant, carbon already present in the soil can be squeezed and heated intensely. The force pushes atoms into new arrangements. Almost immediately, the material cools again, freezing the new structure in place before it can change back. This process does not happen slowly. It does not need clean rooms or careful steps. It is not like cooking something over time. Instead, it is more like a sudden hammer strike. The energy comes from a shock wave that compresses matter and forces atoms into a tighter and more ordered pattern. Scientists link the formation of few-layer graphene in lunar samples to these impact shocks and other high-energy surface processes. This explanation fits well with the moon's long history as an exposed target in space. Understanding this process leads to important ideas about the future. If graphene can form naturally in lunar regolith, then moon dust is not just a problem to brush away from equipment and boots. It could also be a valuable raw resource. Graphene is lightweight, very strong, and useful for conducting electricity. In theory, it could help create strong composite materials, protective coatings, and conductive parts. This matters because sending supplies from Earth to the moon is slow and extremely costly. Every kilogram launched requires time, fuel, and money. Even if early lunar bases only use small amounts of locally sourced materials, producing graphene on site could reduce the need for cargo shipments during the early years of settlement. Over time, this could support more sustainable activity on the moon. There is also a deeper scientific meaning hidden in this discovery. The presence of graphene suggests that carbon exists in the lunar environment in more forms than older textbooks once suggested. It gives scientists another way to think about how the moon formed and how its surface has changed over billions of years. Each tiny flake of graphene carries information about extreme forces and conditions that shaped the lunar surface. Chang'e 6 and the moon's deep past. Chang'e 6 did much more than show that the moon has two different faces. Its findings pointed back to a very early time when the moon itself may not have been solid at all. Scientists believe the most accepted idea for the moon's birth began with a massive collision. NASA explains that a body about the size of Mars, often called Theia, struck the young Earth. This violent impact threw extremely hot material into space. Over time, that debris gathered together and formed the moon. In those early moments, the newborn moon would not have been a cool or quiet object. It would have been intensely hot and almost entirely melted. The heat would have been strong enough to affect the space around it. This stage is known as the lunar magma ocean. The idea makes sense because it predicts a very clear structure for the moon's crust. As the molten surface slowly cooled, heavy minerals sank downward. Lighter minerals, especially those rich in feldspar, floated upward, much like foam rising on a dark liquid. This floating layer gradually hardened and became the bright lunar highlands seen today. Many scientific studies connect the moon's crust, especially in the highlands, to this process called plagioclase flotation. The rocks in these regions are rich in this light mineral and match the chemistry expected from a global melt early in the moon's history. Chang'e 6 strengthened this idea by providing fresh material from the far side of the moon. The soil it collected is not just simple basalt dust. Early analysis shows a strong presence of a northite-rich plagioclase, likely coming from orthosite, mixed with glass and fragments that cannot be explained by local lava flows alone. This mixture suggests that the samples contain traces of an older, lighter crust. Such a crust would only exist if the moon once separated its materials while it was molten. The location of the samples makes this evidence even more powerful. The South Pole Aitken Basin is one of the largest and deepest impact basins in the entire solar system. It stretches about 2,500 kilometers across and reaches depths of roughly 6 to 8 kilometers. Many scientists consider it the oldest recognized basin on the moon. An impact of this scale removed vast amounts of surface material and left the crust beneath the basin unusually thin. Because of this, researchers see the region as a natural window into the moon's deeper layers. On Earth, even the deepest drilling efforts have never reached beyond the crust into the mantle. On the moon, however, a single ancient impact achieved what drilling cannot. It dug deep enough to bring lower crust and possibly mantle-related materials closer to the surface. With no air or water to erase them, these materials remained preserved. This is why Chang'e 6 represents more than a routine mission. It offers samples from deep inside the moon for the first time. A study reported in 2025 identified primitive lunar mantle olivine in the returned soil. This provides a more direct view of the moon's interior than samples from the near side ever could. Other studies also found non-basalt materials, such as orthopyroxene and feldspathic fragments. These findings support the idea that far-side soil is a mix of local basalt and deeper rocks brought up by ancient impacts. Through these discoveries, the moon becomes more than a flat object in the sky. It begins to look like a layered world with a complex early history. Orthosite points to a first crust formed on a global melt. Mantle minerals reveal heavier material below. The South Pole Aitken Basin acts like a deep cut that exposed these layers to view. Yet the results did not only highlight ancient heat, they also raised a surprising question. The laboratory studies hinted at something expected to be rare on a body shaped by extreme heat and vacuum. If the moon began as molten rock, where could water still exist today? Hidden wealth in lunar dust. One possible answer to the moon's value may be sitting inside something as small as glass. Impact glass beads are tiny droplets created when a meteor hits the lunar surface with great force. The impact melts rock and sprays it outward. As these droplets fly through space, they cool quickly and then fall back onto the moon. A 2023 Nature Geoscience study estimated that these beads could hold up to about 2.7 times 10 to the 14th kilograms of water spread across the lunar surface. The idea behind this is simple and powerful. Hydrogen from the solar wind strikes the glass beads, bonds with oxygen already in the glass, and creates water. The bead then traps that newly formed water inside. This means water may exist in places people once thought were completely dry. Another possible source of lunar water is not ice at all. It is water locked inside minerals. Researchers who studied soils from Chang'e 5 reported finding a hydrated salt called NH4Mg3.6H20. This mineral contains about 41% water by weight. The researchers argued that this crystal was not caused by contamination from Earth or from the spacecraft itself. If one mineral can hold that much bonded water, then heating lunar rock and collecting steam becomes a realistic method, not a distant dream. This changes how people think about survival and work on the moon. There is also a complication tied to location. Early analysis reported by the Associated Press describes samples from the far side of the moon that appear much drier than many near-side samples, some measured under 1.5 micrograms of water per gram of material. This does not remove the idea that the moon holds useful resources, but it suggests that water is not evenly spread. Where a base is built could decide whether living and working there is affordable or extremely costly. Geography becomes a major factor. When these ideas are put together, the meaning for future settlement plans becomes clearer. If water exists inside glass beads and hydrated minerals, crews would not need to bring every drop from Earth. Instead, they would need strong power systems, heaters, and sealed equipment that can capture vapor in a vacuum. The main challenge shifts from transportation to industry. The moon becomes a place where materials are processed, not just visited. Then there is the energy discussion that appears in nearly every debate about the moon. Helium-3 is often mentioned. China's Chang'e 5 samples included a newly recognized lunar mineral called Chang'e-Y. Chinese officials announced this discovery after it was approved by the International Mineralogical Association. The mineral gained attention because helium-3 is often discussed as a possible fuel for future fusion energy. The idea sounds exciting, but reality adds limits. Working fusion reactors and profitable mining are still uncertain. Studies of lunar helium-3 show that concentrations in soil are usually measured in parts per billion. This means massive amounts of regolith would need to be processed for very small returns. Even optimistic estimates make more sense as long-term possibilities rather than near-term solutions. Because of this, location on the moon starts to feel political. NASA identified 13 possible landing regions near the lunar South Pole for Artemis 3 Point. These areas were chosen because they can offer long periods of sunlight and are close to permanently shadowed cold traps that may hold ice. Shackleton Crater is in this region. Its rim can receive sunlight for much of the year, while its interior stays dark enough to preserve volatile materials. China is also moving forward with plans. The International Lunar Research Station concept is taking shape, and recent reporting links Chang'e 7 and Chang'e 8 to efforts to scout South Polar water ice and test ways to live using local resources. The language around moon missions has changed. It is no longer just about brief visits and symbolic moments. It is now about building systems that last. That change marks a turning point. The key twist is not that the moon has value, but that major powers are planning as if they intend to stay. Maps, timelines, and hardware are being designed to treat the lunar surface like part of a future supply chain. Exploration is becoming preparation. This raises an important question about who will set the rules before the first factory appears. The moon is no longer just a quiet light in the night sky. Chang'e ASICs helped change that view by bringing home about 4 pounds of soil and rock after 53 days. That return reshaped many assumptions. The samples suggest a moon built from extremes. One hemisphere stayed warmer and poured lava into dark plains. The other preserved its history in bright highlands. The material also points to value in the dirt itself, from impact-made carbon sheets to deep rocks lifted by an ancient basin that works like a natural drill. This is why the current race feels different from the one in the 1960s. Back then, success ended with a footprint and a photograph. Today, it continues with detailed maps, power plans, and machines meant to remain in place. If water can be pulled from minerals and glass, and if sunlight near the poles can power equipment for long stretches, the moon begins to look like a factory site, a fuel stop, and a workshop for the next journey outward. The far side was never truly empty. It was waiting to be understood. Now the questions grow louder. Should humanity mine this world for energy and materials? Or should strict limits be set before the first permanent base arrives? And if graphene can be harvested from lunar dust, could it become the foundation of real cities beyond Earth? Share your thoughts in the comments and don't forget to like, share, and subscribe. Before you go, be sure to click on the video shown on your screen.